that was the response spectrum, a quick one because you already know. Linear time history now is one step next to that one. And this one say, okay, why don't we just run every ground motion and then look for the real results? Why are we trying to use a single degree of freedom concept from multiple earthquakes, general one, not reference to this building? Why don't we use the real one? So that's where it comes in. So now we say, okay, we have this equation already. We have the model. So everything is there that we need. The damping we need is already there. The stiffness is there, mass is there. And ground motions that we use to generate the response spectrum, if we bring those ground motions or we convert the response spectrum into ground motions, either way, you can then input the ground motion directly and then run the analysis. So that's the next step that we just skip. So basically, this is the full dynamic analysis solved in time, but with one simplification, it remains linear. Damage and nonlinearity is not considered. So we take this equation, linear elastic, and then you say the core concept is it preserves the time dimension. Response spectrum time is not considered. So you are taking the response of any time and just saying they are all the same. For example, maximum from this, maximum from that, and doesn't care whether it happened at the start of the earthquake or whether it happened at the end of the earthquake. So one ordinate may be coming from the beginning of the earthquake, another coming from the middle of the earthquake, another one coming at the end of the earthquake. So they have no physical meaning. They never could have occurred together. So if you want to do a real analysis for each time the ground is moving, and then this one, and stick consistently with that, with the correct sign, not taking the maximum, not taking the unsigned values, then we say, okay, we run this one. So this is the actual ground motion input. The word actual is not correct because we don't know the real one. The actual means we take the ground motion which is possible at that point. Simulated, you can say, or from previous ground records. So we take one of those, then we use the same linear model. That's the good thing. We don't need to do anything else. Just same model that you made before, response spectrum. Just change the input from response spectrum to linear ground, and then this will complete the response history. So it will give you the entire response history, and you can get much more information. It's easy. All you need is additional data is the simulated time histories, and that's not difficult. There's a whole peer database with thousands upon thousands of time histories available there. You bring them back, you can scale them to your response spectrum, so they are not outside the range of that, but you still use the ground motion. So that's the thing. So now we get the output. So that's the input, and that's the output. So you get the actual peak. This is the thing, a peak 1 centimeter at 4.5 seconds, which you could not get from response spectrum because it is just taking all the peaks and putting them together. This now you can say, okay, every location in the structure now, every floor, every place, you can get the acceleration, displacement, velocity at every time during the earthquake. That's a lot of information, but a lot of useful information. And the good thing is that the bending moments and shear forces will be corresponding to that displacement at that time in that part of the structure. So and this will be cumulative. If the structure has already moved a little bit and you ground motion, so it will start from that and move forward. So it's not isolated. So the structure's natural response and damping and whatever it is, it will be accounted for in that analysis. So that's the advantage of running linear time history analysis without significant more effort. So what is needed as input? Ground motion records, real or synthetic. Like I said, real means from actual, previous, or synthetic. People can just generate also back from so it's both way. You have a ground motion, you scale it to response spectrum, or for response spectrum, you generate a synthetic one. Tools are available. Linear elastic model, damping model is the same. Integration parameters, you specify how do you want to integrate. There are methods in ETABS we can choose later. So basically you integrate the whole equation, the ground motion equation, to actual structure and get the real results. Only problem is it's linear. So any damage, any cracking, any yielding has not been accounted for. So we get complete time history, time correlated factors, envelope results, and flow response spectra. Very important. You get every floor response spectra, acceleration, velocities, displacement at each floor, at each point actually. And then you also get envelope results. So now you know that you can use the envelope for the whole time history rather than using the absolute response that you got from the response spectrum. So that's the advantage of using the linear time history analysis. And we always recommend people just run it anyway because it doesn't cost you much. So limitations now, let's see what are the bad points, like I was mentioning, why people say response spectrum is not the best way to do this one. Irregular structures where modal combination introduces significant error. So the modal combinations that you saw, rules, are still masking the problem. They're just combining things together by a fixed formula for every structure. But in real structure, complicated structures, modes do not add up in the same way, especially irregular structure. So those combination rules simply miss the peaks or can miss the actual content of the response. So that's the first one. Closely spaced modes, coupled shear walls, and torsionally coupled buildings will not work well for response spectrum. Near fault effects. So near fault is that when the structure is very close to the fault, then the direction is very much clear. There is no second direction effect. Along the fault and across the fault, ground motions are very, very different. And then on a near one, they should be used individually, not combined later through the RSS or CQC, because or the 30, 40%, 30, 100% rule. So the directional combination also rules do not apply. But in time history analysis, we apply different time histories in each direction, which you can get along the fault and across the fault. This is especially true for near fault buildings, which are lying on the fault or close to the fault. Like Manila, just 5 kilometers from the fault. Many buildings are on the fault or very close to the fault. So the response spectrum will not capture correctly those effects. And similarly, buildings in Nepal and other places, where concurrent forces sets are critical for connection design and stability check. This is a big, big problem. When you design connections, for example, then the response spectrum analysis are not really suitable because you are taking the plus minus, but for the connection, the direction of the force matters. Which direction, force, and quantity with which to be combined, it matters. Tension and compression are not the same. So that's why the direction of the force is important to design something, but response spectrum always gives you the absolute value. And you don't know, and you have to use both the direction, which is also incorrect. So these are some of the drawbacks. Of course, practically, like I said, people still use it, and it has a lot of advantages in terms of the simplification. So I will show you another slide later. What is the answer? What is the solution to all these things? Okay. So this is a bridge to nonlinear analysis, which I'll come to that, but basically response spectrum is a starting point anyway. You have to design something to verify. So for the nonlinear model, you need reinforcement to make the model. So where does it come from? Where should we get it from? We have to get it from somewhere. So response spectrum is the starting point where you can do the response spectrum based design, get the reinforcement and sizes, and then move on to the next stages. So it becomes an important design step. So equivalent method, response spectrum method, pushover method, and then the nonlinear time history analysis method. This is the complete design and validation cycle, you can say. So now we equivalent linear force method, which is the code, could be the starting point, or it could be response spectrum. So response spectrum, and they are considered similar because this has to go back. So you have to do this one anyway to get the base shear, which will be used for scaling. So you cannot skip this, even if you use this one, because this has to be scaled back there. So you start with this one, You do this one, you scale it back. Then from there, you can either do a pushover or nonlinear, or you can go to linear and then come here. So this is the way that reliable design can be done. So now we can talk about pushover, and then we can talk about the nonlinear time history analysis also. So we already talked about that. Okay, so this is the flow response spectra that I was mentioning, that the time history, that slide was actually out of place, that should come later. But anyway, so when you do the linear time history analysis, one of the important things that you can get is this kind of a plot amplification, especially for resonance. So we talked about that last time, that if this building has a resonance, response spectrum cannot capture it properly, because it doesn't know the nature of the ground motion. So ground motion's nature has been, I would say, converted into response spectrum, smoothened response spectrum. So if there's any peaks, many peaks in the response spectrum, then many peaks in the ground motion, they're not visible in the response spectrum anymore. But if you run linear time history analysis, you will capture that. So any ground motion peaks which are matching with the natural period of the building, you will get that amplification factor. And that amplification can be captured now. So this is one of the major advantage of running a full time history analysis, that you can capture the resonance effects. Yeah, so we already talked about this one, for the damping and the effect of damping, and this one when we look at the damping, so it's over-damped structure, and then how the damping will change. So this was, we discussed this one, but the damping is still very important in all of that, because we are going to talk about the response spectrum, which will depend on the modes. And of course, for the linear time history analysis, the modes will be automatically determined and included. We don't need any combination rules, because when we are running the time history analysis, we don't need the natural period as an input. It's not one of the inputs. It's just the mass and stiffness. And that's why it captures the actual response. Yeah, so this is the other important thing so far we are using this approach, like I said, no damage, no nonlinearity. So for all of the methods that we have talked about so far, the equivalent static method, the response spectrum method, the linear time history method, we have not counted for nonlinearity. And then the nonlinearity, as you know, will cause damage. So that will change the whole structure, and then that will be captured by nonlinear time history analysis. Yeah, this is just to show you that this is the actual response histories, response spectrum from earthquake, and that is the gold line is the smoothened one. So actual one. So if you have a lot of time histories response, then you need to get the average one, match the response to, scale that response to a given response spectrum before you can use it. Because one of the things that the codes do not want is that you design structures with the time history which is not for the site, or which is not matching with the location. So you cannot just bring any ground motion from the library. Let's say you go to the pier and you take a ground motion with PGA of 1.2, but your site PGA is only 0.5. So you cannot bring any arbitrary ground motion and start using it. You must match it and scale it to fit the response spectrum. So you take the response spectrum of that, match with this one, and scale the ground motion with that. So that's the important step before we use the ground motion, either for linear time history or for nonlinear time history analysis. And now many tools are available, even ETABS can do the matching. Anyway, so pushover analysis is one step in this one. So far, every method on that side has been, and here has been, without nonlinearity. So far, everything that we have talked about, 5, 6 methods, they all are linear, and they have been ignoring the effect of any cracking damage during the loading period. They assume something in advance and they keep it constant. For example, cracking factors, damping ratio, all those things which depend on structural response, they take a value and they fix it and they use it throughout. But now we come to this stage where we want to have this nonlinearity covered, which is the nonlinearity correction covered. That means when we start to load the structure, we know that it's never going to go. You have seen it, the beam that you loaded started to crack and break. So now we come to that one. So pushover is basically that equation, part of that. So in previously, if you look at that, we have done, material has been linear. The loading has been single force set. The output has been one design point, and especially for the compared to the equivalent static or equivalent, the first one. If you compare with that, this is very similar to the first one. That means it is the same concept that you take the structure and you apply a force on it, and the force is assumed to be the pattern of the force is known to be pre-known, unlike the response spectrum or unlike the time history, which is dependent on the ground motion during the dynamics. The dynamics effects are now taken out. And we go back to the statics, the first method, with one change, that now we are not going to use the linear equations anymore. So this was done before other methods progressed too far, because people realized that nonlinearity has to be considered soon. So that's why we are comparing it with the first one. So that was linear, single force, and so on. Pushover is, material is nonlinear, number one. Second one, the loading is incremental. We don't fix the loading. We vary the loading from 0 until the structure is gone or pushed over. So that's where the pushed over comes for. They were pushing the structure until it has fallen down. So if I do this one, that's the pushover method, right? I pushed it until it's gone. So I started with a small force and then I continued it until the structure failed, right? This is exactly what the pushover is doing. So that's an output is full curve, not one design point, but full curve, because we push from 0 force to the maximum force, not apply the force at the design point. Then the mechanism is not identified. This is visible. As you can see, we saw what happened to the structure. Because we pushed it, we know which column failed first, how did the floor fall down, and all of that stuff. So we can see the mechanism, what it will go. And then complexity is from low to moderate. That was very low, the lowest actually. This one is moderate, because we now have the complexity of the nonlinearity plus the complexity of the analysis procedures itself. So that's the pushover curve. So core concept is we apply the lateral load, increase gradually, take nonlinearity into account, identify yielding, and then we obtain the capacity curve versus the base shear. So we apply the force. It's just like what you did for your beams. You just applied it vertically. That's the only difference. So you did actually a pushover test of the beam. So you will get something like this. You've already seen it in nonlinear. In last course, we talked a lot about it. You will get first yielding, peak strength, strength degradation, and collapse. And you have this, we have gone through this many times already, this curve. For the last class, we talked about, So now all of the things we studied in the last class of the moment curvature, of the ductility, everything becomes now relevant. Without that, we cannot proceed. So then elastic stiffness, yield point, ductility, overstrength, everything is now needs to be considered. And now we bring those concepts again and apply them to the whole structure. Before we applied them just to one cross section. Moment curvature is one cross section. We now add it to the whole structure. So basically the codes require that you apply the load in a certain manner. You cannot choose the pattern. The force value is not specified, is not known, but the pattern has to be selected. So they say, okay, the load pattern should correspond to the type of analysis you want to do. You want to do it for earthquake, then you use the same pattern of the load as for earthquake, which is very high at the top and zero at the base. So you use that inverted triangle distribution, and that is coming mostly from first mode. So you take the first mode of the structure and you take the mode shape of the first mode, and you use that as a scaling factor for this load. So the load should vary in the same way as the first mode deformation will be. So you convert the first mode deformation into equivalent load that will come, and then you apply that. Mode proportional, uniform, or multimode. So you also can check the structure for uniform load. And then multimode. That means you check the structure for many modes, one at a time, and then add them together. Because when we started pushover, people started pushover, the first complaint was, what about the other modes? Then there was one student who did thesis with me like maybe 15 years ago or more. When this came out, everybody was interested. At that time, she found that at that time, there are about 14, 15 different pushover methods in practice, all trying to find the best way to combine modes and directions, because the direction problem was there, the mode problem was there. So everybody come up with many methods. So at one point, the most research was done in pushover, and so many methods came up. Now it's gone back again, and only 2, 3 have survived. So basically, you do that proportional to mass only, proportional to the modal deformation, and this is for multimodes. So that's the 3 patterns that you can specify. So once you do that, this is the response spectrum like that, and this one now can be put on the same graph. That's the beauty of this one. So you convert the response spectrum into an ADRC form, the one that you see on the blue, and then you plot so instead of the response spectrum, as you know, is on the natural period scale, but it can be converted into deformation scale. So you convert the response spectrum, transform it in such a way that you plot the deformation on the horizontal and force on the vertical. And then, so this is the response spectrum converted into the ADRS form. And then you plot the structure's push over curve, which is called the capacity curve, and they will intersect somewhere. And that's called the performance point. So that performance point should be where you want it to be. Now imagine that the earthquake is too high. So the earthquake will be above this one. That means your structure is too weak. It never reached the demand. So that means your structure will fail during the earthquake because it never reached. Or they meet somewhere here, and the displacement is too large, unacceptable displacement. Again, or the earthquake is here and the demand is very high over design. So you can check all those things by comparing the response spectrum, scaled response spectrum, and the actual push from 0 to failure together, and then you can get all of the important information. And the codes have a lot of methods to calculate, how to calculate the capacity curve, how to do that. There are methods and methods and methods behind it. And there are formulas for the capacity spectrum method. There are many things to do. It's not, concept is very simple, but application is not. So you basically create the nonlinear structure now, and then you push with the displacement and force, and then you have the response spectrum also converted to the same scale, and then you find this you can actually generate several of these blue curves, one for MC, maximum credible earthquake, one for design earthquake, one for that earthquake. So you can check the structural performance for different earthquake. Or you can say, okay, I have a structure, tell me what earthquake can it resist? So you can check, oh, this earthquake, up to that, no more. Or so you can do a lot of things with pushover curve. That's why we always recommend that you run pushover for the structure anyway, because it gives you a good understanding of what's happening to the structure, because it's simple enough to understand one curve. So you get plastic hinge map. So when you do the pushover, you can get every location of the structure is going to, because you put the hinges there, you can get this curve not only for the structure, for every location. You can say, okay, this hinge is this location, this location will fail first, then that will fail, that will fail. So you get exact map of the failure. So you get plastic hinge map, every location of the structure. Where is it in terms of the performance? Is it cracked, just cracked, or very much cracked, or rotation is too high? So there are normally 4 colors to map this one. And that goes back to the performance indicators. So you get you get the ductility demand because of the length of the curve is ductility. You get yielding sequence, how they will yield. You get the overstrength validation. You also get the difference between the elastic and the inelastic demand, the delta F that we were talking about and any given displacement, because if you plot the linear one here, for any displacement, you can find the difference between them, and that will be your overstrength and R factor validation. Story drift profile, you can get that, and then this is a connection to performance-based design. This actually leads to performance-based design. In fact, this is performance-based design. Also, people use it for many structures. Pushover is enough to call it PBD, right? So that's the pushover analysis in a very different direction than all the other methods we have talked about so far. So once again, why did people stop using it? Same reason why response spectrum has limitations. So it's very similar in that way, that it is very good, but it has limitation. Number one, higher mode effects cannot be captured because doing one mode at a time, modal combination, multi-mode pushover did not solve the problem properly. Same problem with response spectrum, but now with nonlinearity. The fixed load pattern, we already prefix how the load will be applied. Real structure will not be like that, especially in time history. Then single direction path, once again, only one direction we are pushing. What about the other direction? Maybe the earthquake is diagonal. What happened there? The structure is unsymmetrical. What happened there? We don't know. We fix everything before we start the process. And then no duration cycle effects, no damage effect accumulated. It's just one-time push. But actual structure is doing like this. So that is also gone. So it has these weaknesses why people don't use it as the final answer. It is a very good answer, but not the final answer because it still missed so many things. So for tall buildings, people use multi-mode pushover. Like I said, many pushover were developed to capture one of these problems, higher mode effects captured by multi-mode, adaptive pushover, and nonlinearity response history. So this is, of course, we will now go to number 3, the last one, that we don't use pushover, but we use full nonlinear time history analysis, which is the final step in our whole study. All right, so far, all clear? Adaptive pushover is, it changes, it updates the load pattern at each step. So you don't use the previous load pattern. You start with the load pattern, but it updates the load pattern based on the deformation. So it adapts the load, not just use the first load that you started with. Okay, we come to the last step, the highest level now. So this is where as they say, the buck stops. There's nothing better than this one. So if you can do this one, that means you have reached the final stage of the structural engineering knowledge and application. So you basically have gone back to this main equation. So we use the full ground equation now. And now this is the same as linear time history analysis, but it puts together linear time history analysis and pushover together. It takes everything from pushover, it takes everything from linear analysis and combine them together to create this nonlinear time history and remove all of the problems in both of them. So nonlinear material models, fiber hinge, hysterics loop, nonlinear geometry, convergence control, and much greater computational demand, of course. So that it's not going to be easy. And why we waited so far? Because we just didn't have the computers. We didn't just have the computing power to do this one. Knowledge also, software, everything. And now you can see here that this is going to be linear and nonlinear response are now going to be different for the same ground motion, because the damage is now going to change the response after each cycle. So if something happens here, it will affect every. So you can see here it's going to drift away. So this is the after this you plot from here. The structure will drift up to this point. It's no longer on the zero axis. This remains on the zero axis because linear. Go back, go up and go down, doesn't matter. Here it will drift away. That means after the earthquake is finished, there is a residual displacement because the structure has damaged. It hasn't come back to this original position because that is the definition of linear response. This is a nonlinear inelastic response. So if you remember first course, nonlinear and inelastic, it goes nonlinear way, doesn't come back to the same point. So that means the building is no longer where it started from. It will not return. It will be permanently deformed, which is the residual drift, or many other ways that you can measure it. So that's the key difference between first and second response. Not only this pattern will be different, but it will not come back to zero. So this is the rules are there, key demands and parameters, acceptance criteria, story drift, residual drift, important, plastic hinge rotation, cumulative energy, floor acceleration, global stability, all these things now can be checked. You remember I showed you 10 items in the beginning that we must check. This can check all 10 of them reliably if you do it right. But it's very hard, really hard. It takes a lot of time. In the beginning, when we started doing this one for many buildings, they will construct half the building and we will not finish the nonlinear analysis. And they're not waiting for us. So we have to, because they can't wait for 6 months for us to finish the analysis. It normally takes 6 months for a tall building to run this. And so a lot of time it happened that they just went ahead. They didn't wait for us. Anyway, so that's the so now you can see, you can get all these plots of story drift and this one residual drift, and then floor acceleration and the energy dissipation, the performance location. This is a complete picture of what you can get from nonlinear time history analysis. And you know who made this graph? Claude. So Claude knows exactly how PPD, the nonlinear time history analysis works. So the point is that this is the thing that you're looking for a final answer to your building. You have all the answers. You can exactly tell the people on this floor what will be the drift, what will be the drift after the earthquake is finished. This is the limit. This place will crack, this will not crack, this will be red, this will be green, something like that. And you can also show energy, where did it go? Where did the energy go, right? So all these plots will can come out from this one.